Okay, let's get started. So good morning to, I think, probably most everybody. I'm Tim Nedwood. I work for ExxonMobil, and if you're hearing me, you're listening to the webinar series on dispersants and 1 week on herders. So this is webinar week 3. We have 3 very interesting talks today, and I'll get to those in a second. So I want to give a brief introduction so I don't take up too much time here. But as I've said in the past, I wanted to just go through quickly why we're doing this, right? This webinar series allows us to get a broad perspective of folks together so we can listen to different talks on oil spill response and with a particular focus on dispersants. Next week, we're actually going to have is going to be dedicated to the use of herders for in situ burning. But the other 9 talks are on related to dispersants use and issues. All right, so again, it's to allow us to bring a broad range of perspectives together. ExxonMobil and industry's position on oil spill response, especially for marine spills and large offshore marine spills, is that we need to have all tools in the toolbox, and dispersants are an important tool in that regard. But also, as I'll describe, hopefully I'll convince everybody next week that in situ burning enabled by herders is another important tool that's can make a big difference for large offshore spills. Today we're going to hear from, as I said, 3 different speakers. Mary Popovech is going to talk about dispersants and human health. She's a toxicologist with one of our affiliates for ExxonMobil. Then Doug Mitchell will describe some work he's done to analyze VOC data that was collected during Deepwater Horizon and some correlations he made with the use of subsea dispersant injection that was done back then. And then Jan Svejkovsky will talk about some work that he did. He has a small company that was very heavily involved in the Deepwater Horizon incident and taking aerial photographs over the site, and he's going to describe some of that work that he did back then. So the way this is going to be set up is I'm running this kind of like it would be a session during a conference. We're going to have the 3 talks. We'll have Mary is going to go first and describe the work that she's done. So 20-minute talk and then 10 minutes of questions by Mary, and then we'll go to Doug for the same thing, and then we'll go to Jan. So as you come up with questions, as you hear the talks, hit the Q&A button that should be on your screen and type them in, and then at the end of the talks I'll ask the speaker the question and get through as many as we can before we need to move on to the next speaker. And then what we've been doing in the past is staying over for about 15 minutes or so, and to allow some of the other questions to be answered, because I expect we might get more questions than we have time to answer. Several people have been emailing me asking about whether or not we're going to be saving the videos and allowing them to be available and the slides. I'm making headway. There's a new process inside ExxonMobil to get approval to release videos, because there's big data privacy concerns about using those things. So I have to go through a process that I haven't done before, so it's taking a little bit of time. But I'm very hopeful that this week I'll have gone through all the hoops that are necessary, and I'll be able to share that. And my plan is to put this up on a website that's available to everyone, and I'm working with the American Petroleum Institute to try to do it through their website, so it has access. So I can just give out the website address next time, and you can download these videos and talk to them. So I do hope the videos will be available shortly. So let's get started. Let me introduce Dr. Popovech. She is a toxicologist at ExxonMobil Biomedical Sciences, where she leads risk assessments for a broad slate of company products and operations. She completed her doctoral training at NYU School of Medicine in inhalation toxicology and her master's in public health from Columbia University. So with that, I will turn it over to Mary. There you go, you're unmuted. Go ahead.
Thank you, Tim. And I hope everyone can hear me and see my slides. So today, as Tim mentioned, I'm going to discuss human health risk assessment of oil dispersant ingredients. And at the end of my talk, I'm going to give a little bit of guidance for future studies on the topic. So for this talk, I'm going to start off with a little bit of background on what risk assessment is, how we conduct risk assessments. Then, like I mentioned, I'm going to talk about the hazards of Kregsit 9500 specifically. I'm going to do a brief review of toxicology studies that have been conducted on Kregsit 9500 in the last 10 years. And then I'm going to end with some brief conclusions. So risk is one of those concepts that people tend to confuse a bit with hazard. So when we talk about risk, we have to think about hazard being also a function of exposure. And I like to use, the shark analogy. So sharks pose an inherent hazard to human health. They can result in mild, moderate, severe injury, or even death. But when thinking about sharks, hazard is only part of the equation. We really need to think about how are humans exposed to this specific and unique hazard. Is it someone that's free diving in great white shark infested waters? Is it someone that's cage diving, so they have some type of built-in protection? Or is it just someone that's going to see sharks in an aquarium setting? So the risk of those three exposure scenarios look very, very different. But the hazard, which is the shark, remains the same throughout each of the scenarios. So from the technical perspective, how we start off doing a risk assessment is the first thing that we do is try and identify what a hazard is. So when we identify hazards, we look at human evidence. We also look at animal evidence, as well as some alternative bioassays, which I'll term in vitro studies. And we can also look at structure-activity relationships of the specific chemicals involved that we're considering. In phase 2, what we talk about is dose response. So in order to get a better understanding of the hazard, we also need to understand at what doses do those hazards pose a higher risk. So we do that by conducting what we call dose range studies, where we will expose either animals or with alternative bioassays, we look at various doses, a range of doses. We also really need to focus on the most likely route of exposure for humans. So are we talking about dermal exposures, oral exposures, or inhalation exposures? The next thing that's critical that we think about is susceptibility. Are there unique subpopulations that are susceptible? And a great example is children or the elderly. And then we have to think about the chemical in and of itself and how it interacts with a biological system. How is it absorbed? How is it distributed through a system? Is the chemical metabolized? And then lastly, how is it excreted? Once we have those two phases put together, we work with exposure scientists, and then we focus on characterizing risks. Then, if the risk exists, that's where you start thinking about risk management. Can we implement specific PPE to mitigate risks? Can we develop guidelines for people that are going to be using these chemicals to make sure that they remain safe? Or do we eliminate these exposures altogether? So these are, in the end, how we come up with risk management decisions and different options. But for this talk, I'm going to focus primarily on the first two phases, and at the end, I'll touch a little bit on risk characterization. So in terms of hazards for dispersant constituents, I chose to specifically look at Kregsit 9500 since it's very commonly used dispersant. It also has been, the ingredients used in Kregsit 9500 have been used for decades in commerce and various consumer products. And I'll walk through these ingredients. So for the first one, sorbate and fatty acid esters. For this group of chemicals, they're very commonly used in food in flavorings, thickeners, emulsifiers, defoaming agents. They're also commonly used in cosmetics, various pharmaceuticals, and personal care products. Dioctyl sodium sulfosuccinate, again, is used as a food flavoring, and then really its primary use in the pharmaceutical space is in laxatives. So over-the-counter laxatives, you're going to find this ingredient pretty much in all of them. Dipropylene glycol monobutyl ether, it's commonly used in degreasers, various cleaners, paint removers, dyes, adhesives, and then hydrotreated light petroleum distillates are used as propellants and air fresheners. They're used in paints, varnish, and lubricants. So like I mentioned, all of these ingredients very commonly used in products that we encounter on a daily basis. And they've also been extensively studied. So when looking at the hazard data for all of these components, like I mentioned, they've been extensively studied. Most of them have publicly available chemical dossiers that have either been developed for the High Production Volume Challenge and or the EU REACH program. In addition, for all of these, the FDA, as well as the joint FAO and WHO Expert Committee on Food Additives, have evaluated these components for use in food applications. And looking across all of these ingredients, they've either been designated as generally recognized as safe and have also been approved for either direct or indirect food contact applications. And the other thing to note is that through the studies that have been conducted, through the hundreds of studies that have been conducted on these chemicals, none of them have shown to be carcinogens, mutagens, or reproductive toxins. So going through these ingredients, the key thing that I want to point out is when we did our assessment, we looked at acute toxicity, irritation, sensitization, subchronic toxicity, mutagenicity, genotoxicity, carcinogenicity, reproductive toxicity, and developmental toxicity, and in certain cases, neurological toxicity. So for the sorbate and fatty acid esters, what was seen was mild dermal irritation in certain studies, which is not uncommon and would be expected with those end uses, since certain people might be especially susceptible to irritation. For diactyl sodium sulfosuccinate, again, same hazard concern. It's mild irritation that has been reported, all of which is reversible when you stop exposures to the substance. For dipropylene glycol monobutyl ether, we have the same key hazard concern. Again, it's mild irritation that's been reported. And then for the hydrotreated light petroleum distillates, there is a moderate concern. So the moderate concern is what would be expected. You know, if you think about the example of air fresheners, paints, varnishes, when you inhale these in a confined space, you can experience acute narcosis at a high enough exposure. So the hazard is there, and again, we have to consider what the exposure is. Is someone working in a closed room, painting a room with no ventilation, they may experience acute narcosis with the exposure to this specific product. If you're working in open air outside where there's a lot of airflow, air exchanges, you're not going to have the same risk for this hazard of acute narcosis, but it is there. So if anyone wants additional details on this, my paper was published in the IOSC proceedings in the last issue, so I'm happy to share this reference and all of the additional details that come along with it, if anyone is curious. So when we think about toxicology studies, since the Deepwater Horizon incident over the last 10 years, there's really been a lot of work in the space to look at the dispersants used during the response. And of those, many of the studies focused on Krebs at 9500. So when doing a mammalian toxicology study, whether it's an in vitro or an in vivo study, you really need to consider the study design and how you report the results. That's going to be critical in terms of the utility of what can be used in a risk assessment. So when we have to then, you know, take this data, add our adjustment factors, and come up with, you know, an adequate risk assessment, we really need to think about, you know, these specific details for each of the studies that have looked at this substance. So for the first thing that we have to consider the nature of the test substance. You know, are there any unique physical or chemical properties? We have to have very clear description and understanding of the organisms that are being used in the evaluations. For in vivo studies, we really need to understand the number of organisms in each of the groups. We have to have adequate details on the controls. You know, are there positive, negative controls? What controls were used? How were they used? Were they administered in the same way that the chemical was administered? What were the different doses evaluated? Was there one dose, or were there multiple doses to try and assess what is the range of doses that could potentially cause a human health effect? The other really critical piece are the exposure conditions. So were the exposures used, first of all, the same route of exposures that you would expect in a human exposure? Was the chemical applied dermally, or was it aerosolized in an inhalation study? These are really critical to understanding, the relevance to the findings to human health. And then lastly, once you have completed the study, are there adequate macroscopic observations? Are there microscopic observations? And then lastly, when we're assessing these studies, we try and really consider the data quality. So we understand not all studies are made equal, and there are certain ways to code and grade the quality of a study. So one of those methods is using Clemish scores. So what I did for the paper that I published, I conducted a systematic literature review. So when we ran our review, our literature search, we discovered there were about 5,000 different potentially eligible articles on Craig's at 9,500. What we did then is to try and reduce that number to a more manageable number. We excluded articles without toxicology keywords included. So whether they're studies that just use different types of methods that may not be relevant to a toxicology assessment. The next thing that we focused on, we removed articles that were focused on non-mammalian species. So really the key to understanding the human health for this specific literature search that we conducted, we wanted to reduce it just to mammalian species. The other thing we had to exclude were news articles, since those are not directly relevant to a study assessment. And then after removing duplicates, review articles, and conference abstracts, in the end, what we found were 11 in vitro and in vivo toxicology studies focused on mammalian systems, and those are the ones that we reviewed. So again, I'm not going to go into too much detail on these next two slides because I really want to focus on the high level consideration of how we would use these studies in a risk assessment. But if anyone is interested, again, the paper has been published in IOC proceedings, and I'm happy to share that. What we see from this slide focused on the in vivo studies. So there, of the 6 in vivo studies that were conducted on Craig's at 9,500, there were some that were really well conducted using really robust methods. So whole body inhalation, which is an exposure method that we would consider to be much more relevant to human exposures, whereas some other ones used methods like intratracheal installation or inoculation, which has much more limited relevance to humans, especially in the inhalation exposure setting. And I go into the details of why that is in the paper. For the in vitro studies, we see some of the same. So one of the key things that we look at when reviewing a method section for one of these studies is the documentation. So are the methods clearly described? With this particular study, do we know the source of the test model? What's the passage number? What's the details on the culture media used or the culture conditions? These are some basic methodological concerns that we think about, when evaluating the quality of study. And if we even just don't have those basic details, then it makes it especially difficult to then pick up this specific study and use it in a risk assessment. So as I mentioned before, the focus was really on hazard identification, dose response analysis. I covered what all the very basic, information is needed. The primary thing that I can stress is the need for proper documentation in a method section. That way, it can be study can be replicated and or used in the subsequent phase of risk characterization. So in thinking about risk characterization, how do we roll together the hazard identification, the dose response analysis, along with exposure assessment, which is conducted by exposure scientists? So as I mentioned before, what we have to think about is the data quality that's used in the assessment. So we have to consider what's the source of the study, how was the study designed, are the data applicable to human health, and to understanding human health and informing human health impacts. one of the issues is that the more unreliable data becomes, the more uncertainty factors are applied. So typically when we start characterizing risk, we'll take a dose as a point of departure from a study, and then based on various factors of that study. So we look at inter and intra subject variability. We look at, are we extrapolating from an animal species to human? How applicable is that animal species to human? Are we, extrapolating from in vitro, from a cell study? That's very different. And then what type of sample sizes were used, and then what type of endpoints were examined in the study. So when we look at all of those factors together, we have to add in uncertainty factors to basically take that point of departure to come up with, our final risk assessment. And as I mentioned, the more unreliable the data becomes, the more uncertainty factors we have to use, and then the less confidence we have in our final risk assessment. So if we want to make our risk assessment more certain, if we want to have more confidence, what we have to do is really focus on understanding the mechanism of action of the chemicals. That can really help, and we do that with technical research. We can also start using what are called physiologically based pharmacokinetic models that look at distribution and metabolism. And then one of the other things is increasing the sample size and or repeating the experiments. So the more experiments that we have, the more confident we can be in the results of these studies. So in conclusion, it's very clear that these dispersant components have been manufactured and used in US commerce for decades. So these are commonly used chemicals in consumer products that we all encounter on a daily basis. The specific components of Kregsit 9500 have been studied extensively, both on their own, and then now collectively, they're starting to be studied as well. Kregsit 9500 hazards, so we have several constituents, three of them, or three classes of them that produce skin and eye irritation. That's very clear. The hydrotreated light petroleum distillates, we have a very clear understanding that they may produce acute CNS effects at high doses and typically in confined spaces. And when we think about risk mitigation and risk management, we believe that use of personal protective equipment that would prevent exposures would really work to minimize the risk to spill responders. And then after reviewing both in vitro and in vivo toxicology studies, there are quite a few examples where the study design is not inherently transparent in the papers that were published, which really lead to a lot of difficulties in evaluating the study quality. It's really important that any scientists that are trying to examine dispersant materials, that they understand the body of the scientific evidence. So focusing on chemical specific information from the dispersant ingredients, along with studies of the whole product. And then for these in vivo and in vitro toxicology studies, they should really focus on trying to choose the most appropriate high quality study designs, choosing the correct routes of exposure, choosing a higher number of organisms to test. That way the studies can be really applicable and more adequately inform risk assessments. And now I'm happy to take any questions.
Thanks, Mary. That was great. We have time for questions, so feel free to submit them. Well, I guess I'll start off with a quick question, Mary. So this analysis you did was completed back in what, 2017 or earlier? Yeah.
Yes.
I imagine that it's probably time to kind of go back and look in the literature, because this is a very, in the last 3 years, there's probably been maybe as many papers that have been published. So so it's something that we should think about. I'm not sure if you've been keeping up with the literature very much since you finished this, but that's something that we should think about it, for maybe next time we give or write a peer reviewed publication outside of IOSC.
Absolutely. The pace of science moves so quickly, and there's been so much funding specifically on dispersants. It's completely warranted to continue to update these literature surveys and assessments.
Yeah. Okay.
Again, the paper has been published in the IOC proceedings, and if anyone has questions after this talk, I'm sure Tim could share my contact information.
Yeah, so yeah, if questions come up, continue to put them in. One more question. So I guess, when you looked at the literature review, the slides, and I'm not sure how much detail you went into this, but you narrowed down over 2,000 papers to just 11?
Yes, so a lot of the studies that have been conducted, the majority of this research is focused on environmental effects and marine organisms and things like that. So there's very little research at this time when we did this literature search that was focused specifically on mammalian species. And the reason we decided to focus on that is we wanted to look at human health specifically, and some reports of issues with inhalation related impacts related to dispersants. So that was really what we're trying to target, is things that would be the most relevant to inhalation exposures for humans.
Okay. All right. Well, we got a question here. If components have been tested separately and are well documented, is there a likelihood that the combined components react differently and cause a potential different hazard?
It's possible. And that's why, it's really important, specifically, let's say for the inhalation route of exposure, to consider new in vivo studies. So, studies that look at whole body inhalation of an aerosolized product are important to do, and, to have it be the most relevant to human health. Absolutely, it's possible.
Okay, here's another question. Have you looked at the primary breakdown products of core exit in the surrounding environment?
So I'm not sure that any of those studies came up in our search. It's quite possible that those studies have been conducted or looked at since 2017, but to date, once this was published, we did not pick that up in the literature.
Yeah, and I'd suggest that maybe for direct human health issues, right, the breakdown products probably are less important, because it hasn't been time for that kind of activity to happen. That's right. So it's probably your exposure route is more likely to be the primary components of the product.
That's correct. When we think about exposures, again, I'm not an exposure scientist, but the exposure scientists that we have worked with, like Wolf Konkel, that are really experts in the field, they've identified that the most likely route of exposure that would be a concern for human health is, let's say, spill response workers loading dispersants onto planes or things like that. There's wherever potentially an aerosol could be generated with, a very, very close, very direct contact for humans. So it's a little less about the breakdown products.
Yeah. And I'd suggest that for environmental effects, though, the toxicity tests that we talked about last week with Tom Parkerton, those breakdown products, so the biodegradation of the components in those mesocosms and those systems that are undergoing toxicity tests happen, right? So those breakdown products are a component of the testing that core exit 9500 and other dispersants undergo, and the crude oil itself undergo in toxicity tests to some extent. Okay, well that's perfect, right? We're staying on time. So Mary, thank you for that. Why don't you unshare your screen and we'll move on to Doug. So Doug Mitchell works for me here at ExxonMobil. He's going to talk about this very large database of VOC data that he's been analyzing for the last 6 months, and has come with, I believe, are some interesting findings. So he's going to describe that. Doug, you want to hit? There you go. So Doug has a BS in geophysics from Boise State University and a PhD in physical oceanography from the University of Rhode Island Graduate School of Oceanography. He did research at the Naval Research Lab prior to joining ExxonMobil. He currently works in my group in the oil spill response research, and he dabbles in methane emission abatement work, which is his dabble job is becoming his full-time job here recently. So with that, I'll turn it over to Doug.
Thank you. Thank you, everybody, for being here. If you didn't catch it, it's kind of a little humorous, but I got a BS in geophysics from Boise State, which if you really break it down means I got a BS degree from a BS university. Sorry, a little sad humor to start things off. Yeah, so there was data available out there that we were able to get our hands on to look at the effect of subsea dispersant injection on VOCs in the atmosphere and the potential for increasing safety and reducing the exposure of well control personnel that respond to a spill like the Deepwater Horizon event. And that's what I'm going to talk about today. So the overarching goal, the Deepwater response, and also to any other large response, is really to cap the damaged well, drill relief wells, fully shut in the reservoir, and then of course to mitigate any damage to the environment. The picture we're looking on to the right shows one of the aircraft captured pictures, and Jan's going to talk about those a lot more in the next talk, showing a time when there was no SSDI going on and there was a large oil slick at the surface. And the oil slick is very clear. If you look at a time later after SSDI had been turned on and had been going for approximately 11 hours, you can see that there was significantly less oil on the surface. And so there's a lot of anecdotal evidence from these kind of pictures and also from some of the folks working on the vessels themselves that noted when SSDI was going on and it was going on steady and continuing, that there was significantly less oil on the surface of the water and then a resultant reduction in VOCs that were encountered by personnel as well. And so we wanted to try to take this from a very qualitative, there's a picture and somebody said the VOCs were less, into a little bit more quantitative footing. And that's what this work is about. When you really get down to it though, always the number one thing is always the safety of personnel, particularly human life, health, and safety. A lot of the times, the first people to show up out there, and these are the people out there to try to get primary well control taken care of, face the most severe conditions because there's been no response effort. A lot of the times it's when you have max flow coming up, you got max oil coming up, and so they have the potential to see the most adverse atmospheric conditions, particularly such as high VOC concentrations. And when they're there to continue working out on the deck, they have to wear restrictive PPE, which then can slow operations and reduce their ability to respond as effectively as possible. So what we want to really look at here is, did the use of SSDI reduce VOCs, and was it significant? And that's the questions I'm going to attempt to answer. All right. So SSDI was very first approved for its very initial use during the Deepwater Horizon incident in early May 2010. It had not been used prior to that. Due to some logistical issues with the injections and also regulatory constraints, it was an average SSDI rate during the operations of 7.8 gallons per minute. Now, assuming a constant release rate of 37,100 barrels per day, it's a simplified assumption, but we don't have detailed analysis of what the variable release rate was over the course of the event. But using the court-determined total volume that was reduced in the 87 days that the event occurred, it comes out to be an average of 37,100 barrels per day. So using that number, that gives us a dispersant to oil ratio of 1 gallon of dispersant to 140 gallons of oil. That kind of gives us the baseline DOR that we're talking about during the overall response. Now, we know effective SSDI reduces the size of the oil droplets by changing the interfacial tension between the oil and the water. And when they reduce the size of the droplets, it reduces their rise velocity, which has two effects. The first effect is it actually will increase the volume of oil that is dispersed subsea. So what that means is you shift the distribution of oil droplets to smaller and smaller sizes, a larger fraction of them become small enough that their buoyancy and rise time is so long that they can't overcome ocean turbulence, and they may never rise to the surface, and then they can be biodegraded in the water column. Then the other thing that happens is oil tends to then be transported a lot farther from the leak source in the background currents because they're being acted on by the background currents for a much longer time. And then that also allows turbulence to further diffuse the amount of oil in any given volume of water, so it spreads more laterally and vertically as it's rising to the surface farther from the source. And then when it does finally make it to the surface, it's spread out over a much wider area, forms much thinner slicks, and doesn't really interact with the area above the relief point. So again, both these things reduce VOCs above the release point or directly over the wellhead. Now, there has been some subsequent research done that shows that the DOR of 1 to 100 or greater, e.g. 1 to 75 or even 1 to 50 is required for SSDI to optimally disperse oil. If we looked at the 1 to 100 and the amount of time that the DOR was over 1 to 100 for the 3,700 barrel per day estimate, it was only about 8% of the total time that SSDI was in operation. And once you kind of hit that point where you're at the optimal 1 to 100 and you start going to less, it rapidly rolls off in effectiveness. So we were spending some time with the SSDI rate on the rollover of that curve, showing that the SSDI was probably less than optimally effective, but it did still help. All right, so the data that we had to work with came from several sources. One is the GRID-C, which is the Gulf of Mexico Research Initiative Information and Data Cooperative. And there were two sets of data that came from there. We had daily average SSDI rate, so that's just the 24-hour average for each day, so one data point per day. And then we had personal sampler VOC measurements. So these were collected by samplers that individuals wore while working on the vessels over the course of their shift. So it's like a 12-hour sample of the air, and then it's sent to a lab, and it's determined what the average concentration is seen over the 12-hour shift that the instrument was worn. This was the first data sets that I was able to get a hold of and do some basic analysis with. And even though there's some issues with bias in the sampler data, because there were mitigation strategies in place that personnel would go indoors or out of any high VOC concentration environments, and so the peaks are muted and they're not directly tied to SSDI. Even then, there's still some inclination in that data that indeed SSDI still reduced the VOCs that were seen by the personal samplers. So that kind of gave me the first clue that this was worth looking into. And once we determined that, then we went and started seeing if we can find other publicly available data. And there were two sources where we got that. So we got some high resolution SSDI data from BP via RPS, which is a vendor in Rhode Island that does a lot of oil spill response work and modeling. And they use this data to do some modeling with. This data is variable resolution. What it really did is it labeled within the minute accuracy of when SSDI was started, when it was stopped, and when rate changes occurred. So it gives us a very high resolution data of what was actually going on with the SSDI. And then it didn't cover the entire range of the spill event, and I'll have a plot that shows you that in a minute. And then we also had the NODC Scribe database. I think NOC is National Oceanographic Data Center. They had area array VOC measurements. So these are instruments that were deployed on vessels that were working in the area and collected data continuously, and the link for where to get that data set is there as well. And again, the issue with this data is it doesn't cover the whole entire response period, even though area arrays were in operation. This was the only publicly available data that we can get our hands on. All right, so SSDI, the data we're used is shown below on the plot. And there's going to be a lot of plots that have that x-axis with days along it. Day 0 is May 16th at midnight, which is just after they started regular SSDI operations, and we're going to refer to that as day 0. So prior to that, there was not regular operations, and post time 0, there is regular SSDI operations. You can see in the middle, starting at about day 17 through about day 49, that's the high resolution data that we were able to get that very accurately detailed, particularly the on and off times. And you can see how many times it was off and the rate drops down to 0. And there's a lot of high variability in that particular data set. And then the coarse stuff on the tail end and on the beginning end is the daily average data. And so there's only one data point per day in that particular data. So that was the SSDI data that we had to work with. And the problem with the coarse stuff is you got to imagine that if the high resolution stuff you have later is that variable, there must be more variability in the data pre and post, but we have no way of knowing because we don't have high resolution data for those times. Little talk about the area array instruments. It's what they call a photo ionization detector, or a PID. So what it does is it has a pathway where it draws air through it And then it has a high intensity ultraviolet light that is putting out energy at 10.6 electron volts. And then we'll ionize any organic compound that has an ionization energy that is below 10.6 electron volts. So it's not species specific, so you can't isolate specific hydrocarbons. But in general, the larger molecules or molecules with more double or triple bonds, they tend to ionize easier. Very small type molecules, they don't tend to ionize, but most of those molecules were actually solubilized in the water column before they got to the surface. And other instruments that were able to measure for those things showed that there was almost none present. So the area array, as far as we can tell, collected all the necessary VOCs that were in the atmosphere that were there to be measured. They monitored continuously, and their accuracy is from about 0.01 up to about 2,000 parts per million, and then above that, they're ineffective. So we kind of got a cap on the largest that we could potentially measure. And again, due to the depth, most of the small stuff that it doesn't measure were solubilized and didn't make it to the atmosphere anyway, so we're pretty confident that these were doing a pretty good job of capturing the VOCs of interest here. So overall, there were 94,816 measurements collected on 20 different vessels that were operating within the SIMOPS region, and that's the region called the Simultaneous Operations Zone. That's a 5 nautical mile circle around the wellhead location on the surface. So this were all boats that were working within that 5 nautical mile surface area, which is basically all the primary response vessels. The ships in there to drill the relief wells and any boats supporting those, and anything else we're operating in that area. So that's the key area we're focused on. Now, the area arrays do collect continuously, but the data that's in the database available is a 15-minute average, and they report those once per hour. So we have an hourly 15-minute average is what's available to analyze. So there could be spikes that were higher than this, but we don't know because we don't have the raw data available. But you can see the median concentration in there is fairly low, meaning that most of the vessels were measuring most of the time low values. The mean concentration is a bit higher, and then the maximum concentration is measured here, 1,948.6. There could be values that were higher in the raw data, we don't know, and anything above 2,000, the accuracy rapidly falls off, so we're not sure if there were anything higher than that anyway, because they couldn't be accurately measured. To give you a feel for the temporal coverage of the vessels that were operating in the area, this shows the times that they had area arrays on them that were actively collecting data. And you can see we have good temporal coverage from about day -14 up to day about 36. And there's always multiple vessels collecting data, so there's no time where there's just one vessel collecting data, and that's really all we have. There's multiple vessels collecting at every time step along the way. So we have pretty good temporal coverage of the SIMOP zone based on these vessels. Problem with the vessels, they're moving around all the time. A lot of them, most of them were not just sitting still, and we don't really have the data for where they were. And so what that necessitates is we're going to end up treating the SIMOP zone as a control volume. And so now we know what the measurements are within this control volume, and we know what the SSDI is, so we can start to relate what's in the control volume to the SSDI rates. So that's why we ended up doing that way, because there's no way to get a solid control on all the variables you need, and so the control volume is the best way to do the analysis. So if you look at the plot, this is all 94,816 points plotted, and you can see it times 0. Prior to that, the median is quite a bit higher than after that point, and the mean is quite a bit higher than after that point. And just by a quick look at it, you can see that there's a lot more large spikes in the early part before day 0 than there is after the fact. Once the SSDI started. Now there are some operational things occurring during some of these spikes, like out towards day 18, where you kind of see a bit of things spiking up. And that's like when they were putting the top hat on and other things like that, where things were interrupted in the SSDI and there were changes in the operations that led to some increased VOCs at those times. So it's pretty tightly tied to the data. All right, so I'm going to delve a little farther in. If you make if you make the standard assumption here that VOCs are going to be inversely proportional to our SSDI rate, and that's kind of the point of doing SSDI. The higher the rate, you expect the lower the VOCs. And if you kind of look at how we plotted the data there, we have the median hourly VOCs when there's 0 SSDI, those are the black dots, there's 140 of those hours. We have the green dots, which are what we would call partially dosed. The DOR was less than 1 to 100. There's 483 in the green. And then we have the times when it was what we would consider optimally dosed, and there were 56 hours of that data there, and those are in the red. And you can see that there is a diminishment overall, particularly in the larger values of the VOCs as SSDI rate goes up. So that gives us some confidence that indeed there is a relationship here. If we look at just, again, the basic statistics, you can see, prior to SSDI, normal operations and post, drop in the median, drop in the mean, and a significant drop in the 95% non-exceedance value, which is the value for which 95% of the measurements are below this value or 5% above this value. So basic statistics suggests that there is a change, but we took that a little farther and we looked at something called Mann-Whitney non-parametric statistics. We applied the U-test to the 2 different subsets of the data. One is SSDI equals 0 or undosed, or times when SSDI was what we would consider optimally dosed when the DOR was at 1 to 100 or higher. What the Mann-Whitney test does, it looks at it as a distribution, and it checks to see if there are distributions with the same or different medians. And the sample groups show by the Mann-Whitney test that they do indeed come from different medians at the 95% confidence level, which is a standard confidence level used in statistics, and that the median VOC value of the 0 SSDI rate was definitely the one that was higher. So in other words, with no SSDI, higher median, and is statistically significant, and that median is higher than when the DOR was at the optimal level, also at the 95% confidence interval. So that then confirms the basic statistics, takes it to a different level, and confirms that indeed there are different distributions with different medians. So we also looked a little bit, because obviously we're really concerned about personnel safety. So we looked at the reduction of extreme VOCs, and we looked at VOCs that were greater than 500 parts per million, and made the assumption that these may be an immediate health risk. So this requires just a little bit of talk. So there is no OSHA value for just total VOCs, which is what the area raised measure. It's not species specific, so we can't select out one and look at one. But there are OSHA permissible exposure limits, and TWA stands for total time-weighted average, that show for many of the lighter components that would be components of the VOCs, they list 500 parts per million as their permissible exposure limit. So even though it's not for total VOCs, it's for individual components of VOCs, we use that particular value to look at extreme VOCs here. And we don't know if this is a protective value, so we don't know what the exposure limits is for total VOCs. But this is just a number we selected because at least there is some information out there of specific components that are likely to be in the atmosphere over an oil slick. So if you look at what the SSDI operations did to these extreme values, you can see the number of measurements prior to the start of SSDI, which was 55 spikes over 500 parts per million out of 13,000 or so measurements, down to 10 of them out of 80,000. We went from 0.4% to 0.01%. So we reduced the number of the percentage of spikes by a factor of 40. So a very significant reduction in high VOC levels, which would potentially be a risk for personnel. And you see, again, we went from approximately 4 times a day prior to the start of SSDI down to about 0.3 times per day after that. So again, it's a significant reduction in those peak VOCs, which is something we're concerned about because we're concerned about health, life, and safety, and also long-term and short-term risk. So we took the analysis a little farther again, based on that expectations, the inverse relationship between the SSDI rate and VOCs, and thus VOC accumulations. We looked at the accumulation of VOCs, which is shown in the blue line, and the accumulation of 1 over the subsea dispersant injection rate, which is the orange line. Now, there's one issue with that approach, and when you have 1 divided by 0, which we have SSDI rate, times where it's 0, obviously you can't have an infinite accumulation rate at those times. So what we did is we did an optimization and found that if we set a minimum SSDI at 1.1 gallons per minute, it optimized the curve fit, and really what that did is set, this is the maximum accumulation rate that we were seeing in the data when SSDI equals 0, and that set that to that value. And so we're not having spikes up to infinity every time we go to 0. Now, there is the thing that we're going basically from 0 to some set number, and both of them are accumulating to their max value. And you should expect to see some strong correlation between the two. I did detrend the data. So I took out that long trend from 0 to its max value and looked at just the variability on those curves. And that R squared value is still 0.9, meaning that the variability beyond just the linear climb from 0 to the max number is still highly correlated between the two. We also had that really nice fit here between day 3 and 18. And that's the time when the SSDI rate was pretty much a flat 10 gallons per minute for that whole time with very little change. And the curves are sitting over the top of each other very nicely. So number one, when it's very steady, we have a very tight match. And then the other thing, when we remove that long trend out of it, the linear trend, and look at just the variability, the correlation is still 0.9, showing that when SSDI rate is dropping and falling, the VOCs are also inversely moving with that, with a R squared of 0.9. So again, that's showing that SSDI is constraining the VOCs. Otherwise, there would be no need for them. There would not be that level of correlation between the detrended data. Now, if we take what we learned from that and look at the accumulation rate as a function of the SSDI rate, or the inverse of it, and then translate those out over time, you can see we got a bunch of different curves here on this plot. The black line is the actual VOCs accumulated over time. Time 0 is when we started our regular SSD operation. So if I take the mean dosage rate over that time, that's the green line, you see it, there's some variability in the black line because there's variability in the SSDI, but the green line starts and stops at the same point. It's showing that the median value gave us a certain amount of accumulated VOCs. You look at the blue line, that's our estimate. If we didn't dose at all, the line would have kept climbing up like that, would have accumulated that much VOCs in the SIMOPS region. And if you look at the optimally dosed, which is the red line, that shows we would have had a significant reduction in the VOCs if we could have optimally dosed over the entire response period. And then the pink line at the lower down bottom shows if when they got out there and they were ready and they could have started the SSDI as soon as possible at the optimal dosage rate, that's our estimate for how much we could have reduced the VOCs that accumulated in the SIMOPS zone. All right, so in summary, we were able to take this somewhat disparate set of SSDI data and VOC measurements, and we were able to use that to determine if SSDI did significantly reduce VOCs. And we showed using some different statistics that indeed there was a reduction in VOCs when SSDI operations began relative to before they began. Very strong correlation between the inverse SSDI rate and the accumulation of VOCs, and that is still 0.9 even if you remove that linear trend that occurs for an accumulated value. So this does indeed confirm that SSDI rates with sufficient DOR reduce accumulated VOCs. And we also then suggest that starting the SSDI with dispersant to oil ratio of 1 to 100 should commence as early as possible if there's another event to maximize VOC reductions. So the total conclusion, when it's applied at the optimal dosage rate, we can help protect people from acute and chronic VOC risk by drastically reducing the amount of VOCs that accumulate in the SIMOPS zone where people are going to be working over the vessel, and you should definitely initiate it as quickly as possible to maximize the reduction benefits. All right, that would be it.
Okay, thanks, Doug. That was great. We have time for a couple of questions. Let me just start by saying that this is as an ongoing effort that Doug's kind of spearheading here with others. So it's great we have the opportunity to present it this big group, but we do intend to put together a peer-reviewed publication. So stay tuned. That hopefully within the next 6 months or so, depending on how long it takes, we'll have something that gives you more details about what Doug's done. Let me start with a quick question, Doug. You've looked at some of the other kind of variables that could influence the VOC concentrations over the surface. Can you give a quick comment on how those correlate with the
Yes.
with?
So I definitely was able to extract wind data from the closest buoy that's out there that's actually fairly close to this area. And there's almost no correlation between wind speed and VOCs or wind direction in VOCs. And so this is definitely not a wind-driven issue. Somebody asked a question here about application of surface application, and the answer to that question is yes. I do have the time series of that information, and I have looked at it. And when we looked at that accumulative curve, there's times when those curves kind of separate from each other a little bit. And that's because when the area array started measuring a given level of VOCs, the vessel that had the surface dispersant application equipment would drive up and start spraying dispersant applications or use a water cannon to knock the oil back into the water column and drop down the VOCs. And so in some of these cases, the spikes may have gone a lot higher without the application of the surface dispersants or the water cannon. And so at the highest spikes, there may be a little bit of a decoupling to how high they really would have been because of the application of surface dispersants. So yes, there is a little bit of an effect, but generally based on the analysis we're doing, those were at the higher levels, and so the analysis still holds pretty tightly. And the next question down is about the possible that SSDI caused oil to be transported further away. And yes, indeed, that is one of the benefits of SSDI. It disperses oil into smaller droplets, gives turbulence a much longer time to act in the water column. So the oil droplets become more and more diluted, separating from each other, and eventually they can rise to the surface, the ones that have enough buoyancy to do so. But they don't really form a full-on surface slick or nearly as slick as they would if they came right up in the CIMOP zone without any SSDI. And so again, even if they do come up, they're far away and they don't really have an opportunity to introduce VOCs into the CIMOP zone, which is where all the primary response is occurring. And so that's where we want to make sure we're protecting the workers as best as possible.
Okay. Hey, thanks, Doug. We need to move on to the next talk, but maybe we can come back to some of these. There's still 3 or 4 more questions. We can come back to some of these at the end, but I want to make sure Jan has time to go through his slides. So if you want to unshare, Doug, we'll get.
Oh, yep.
We'll get Jan's slides up.
Okay.
So as I mentioned, Jan is going to give a presentation on work that describes some of the work that he did during the Deepwater Horizon incident to take aerial images over the entire spill location. But I think the focus of the talk will be over the well site. So let me give a brief introduction for Jan. Jan did something that for me when I was in graduate school was something that I dreamed of, right? To come up with an idea that I was working on in graduate school and take it into the real world and commercialize it. So Jan did that. He founded Ocean Imaging Corporation while a graduate student. It was originally focused on fisheries-related research and operational applications, but the company expanded into various areas of ocean coastal environmental monitoring with satellite and aerial imaging. So Ocean Imaging has been active in oil spill remote sensing since 2005. During the Deepwater Horizon spill in 2010, Ocean Imaging flew 1 to 2 missions almost every day for 3 months, and was the only provider of image-based oil thickness distribution map products to the response community. So with that, I'll turn it over to Jan.
Okay, can you hear me? Can you hear me?
Sorry, Jan, I was on mute. I can hear you and I can see your slide. Go ahead.
Okay. All right, thanks everyone for joining. What I'll do is give a little bit of a background about our technology, and then discuss its application specifically to dispersants. So My company, since the late 90s, had various aerial multispectral imaging systems that we used for a variety of research and operational applications along the coastline and along the ocean. And in 2005, several organizations actually approached us asking whether the aerial system could be utilized to map oil spills, and particularly to map the thickness of the oil, so that the areas that potentially have the best possibility for recovery could be readily identified. So we started working on that, and the approach that we took was to develop a easily deployable portable system that does not require a dedicated plane like most of the European systems do, and to not reinvent the wheel, to use the same proven thickness estimation principles as visual oil spill surveys do, with additional capabilities that the human eye doesn't have, like thermal imaging. Back then, and to a great extent still today, aerial visual surveys or photo surveys are the most common method of assessing an oil spill. So what we wanted to do is essentially computerize that, with the advantages that a algorithm in a computer is objective and does not rely on opinion and differences in expertise of the operator doing the survey. The human eye obviously can only see in the visible part of the spectrum. Additional cameras can be added, such as thermal IR or ultraviolet, which, as you'll see, is actually very helpful in characterizing the oil thicknesses. The survey map, the product coming from a system like this, is in digital format as a file. And so it can be utilized in a variety of GIS software and allow its direct computation of the oil spill area and volume and other variables. And then finally, the system provides much greater detail than generally the either hand-drawn or photo located GPS located photographs do. We generally work in 1 to 3 meter resolution. So the approach to the algorithm, both for example, the Bond Agreement Oil Appearance Code, to characterize the thickness of a specific oil target. The problem with both visual and trying to do a digital algorithm is that the water background attenuates the color of the specific oil target, and that attenuation is very different if the spill is in the crystal waters of Hawaii or if it is in the sediment-laden waters coming out of the Mississippi Delta. So our approach is to compute ratios between individual wavelength channels in the color UV through near IR spectrum, and then compare those ratios to ratios of clear water background in the surrounding area, which then accounts for the specific locations, characteristics of the water affecting the oil. So here's an example from one area that we used extensively to develop the algorithm and validate the algorithm, the Santa Barbara Channel in California that has natural oil seeps. This is a blob of naturally seeped oil, and you can see that this is a photograph, and you can see that color changes from the outside, which is essentially silver sheen, extremely thin, to then going to rainbow sheen, and then progressively getting thicker into the interior, what the Bonn Agreement would classify as true oil colors. This is the result from the system's algorithm. On the left is the result from the visible cameras or visible wavelength channels. And you can see that it's very sensitive to thin oil films, and the different relatively thin films can be separated, but the interior then maxes out. And basically after about 0.1 millimeter, 0.15 millimeter thickness, you can certainly identify the oil, but you can no longer tell how much thicker than that limit is. On the left, on the other hand, is a thermal image that does not, or is not sensitive to the very thin oil sheens, but on the other hand picks up much more detail in the thicker films, and thereby extending the measurable range of thicknesses that the system is capable of. So looking at basically the different components, or comparing the different approaches, this photo is of part of the Deepwater Horizon spill. And it actually doesn't do justice to the true, say, visual assessment. This is taken from 12,000 feet, and most days the haze over the Deepwater Horizon spill was extremely strong, so that this is a photo that was actually enhanced contrast stretched in Photoshop. An observer, especially at that altitude, would not even see the detail that you can see in the photo. It appears in a combination of the digital multispectral system, which brings out not only greater detail, but much greater changes of color that are oil thickness dependent. And then on the right is, again, the same area imaged with the thermal sensor. Now, the thermal sensor distinguishes oil from water based on primarily one characteristic. The dark areas are thinner oils that appear actually cooler than the surrounding water, and the white areas are the very thick oil that because of its thickness, the solar heat got trapped and actually creates or causes the oil to be warmer than the surrounding water. So this is a picture of the actual system in twin otter aircraft that NOAA essentially gave us or lent us with 2 crews for the entire 3 months that we were working on the spill. You can see a lot of wires and several, separate components. Since then, the second generation system that we use now, the drop-in type unit, the original system actually had some of the components compared to what we use now. For example, the thermal camera has 4 times now the resolution of what we flew in Deepwater Horizon. So we used that system on several spills in California prior to Deepwater Horizon. And so we were kind of known in the community for what we are capable of doing. And then when Deepwater Horizon happened, BP and NOAA requested that we go down there and do our stuff. So we got there in the first few days of May and started producing analyses of oil thickness. Now, by the time we got there, already the spill was so big that there was no way with our equipment and with the aircraft available to every day image the entire spill. So we were basically directed each night for what targets we should go to and image the next day. And especially in the beginning, the source site was obviously a high priority. As time went on and the oil began to hit the coastline in various areas, some days we were not able to image the source because we had to fly at some point as far as Texas or the Florida Panhandle and do imaging there. The image on the left is essentially a true color type analysis, which then we also applied our algorithm to and distributed actual oil thickness maps, which were the first time that anyone has actually provided this during an oil spill. So very shortly after we started this, their requests started coming in from the various factions of the command post to have us do various imaging missions. In one case, just a few days into our stay there, we were coordinated with an aerial dispersant aircraft to see how our technology could help document the effectiveness of aerial dispersants. It was a very good idea, which unfortunately partly failed because while our pilots coordinated very well with the dispersant aircraft, we were also trying to coordinate with a vessel to take field samples in that area. And when everything came to and the dispersant was applied, we finally got a hold of the vessel and found out that they're tens of miles away from the area they were supposed to be in, and they're doing something completely different. So unfortunately, we were not able to add field measurements to it. But what you see here is a photograph of, on the top, untreated oil, and on the bottom, dispersed oil about 20 to 30 minutes after the application. And what the photograph already shows, first of all, the untreated oil actually wasn't completely fresh oil. As you can see in the orange color, it was partly emulsified, but the dispersant caused, as you can see on the bottom, a change not only in the color, but in the texture, where you can kind of see it dispersing into the surroundings. Now, this is what the imaging provided. On the top is on the an area of undispersed oil, and the A and B zoom-ins show the multispectral visible signatures, and then on the right, the B zoom in is the thermal. And the undispersed oil is very prominent in the thermal, as I showed you before in that one other example. Now, the important thing to note is that the thermal camera images literally a few microns of the water surface. It does not penetrate at all. So what that means is any signal, any oil signal that is detected by the thermal imaging sensor is truly on the surface of the ocean. So looking then down in the C and D zoom ins in the area that was hit with dispersant by the aircraft, just like in the photograph, you can see the dispersed oil has a different texture and a change in color, but most importantly, in the thermal image, there is no signal at all, meaning it actually is subsurface. It is no longer floating on the surface. So based on this, we then got a call a day or two later to actually do multiple daily flights during the initial test of subsurface dispersant injections over the well. And that's the timeline here outlined in red. The blue line is a daily average of the subsurface dispersant injections in gallons per hour. And the dots on the bottom, by the way, are, I'll come back to those in a minute, but those are days that we actually have data from our system flying over the source site. So before, you saw this in the previous presentation, before the dispersant was applied, the source area had a lot of dark, i.e. thick, fresh oil in the vicinity. And then this is the sequence during the dispersant, the test release of the dispersant. So one thing that must be kept in mind is that the very, very deep water column caused the delay between when the dispersant began to, when any effects would be expected on the surface. The lag between the two line, but we were working with estimates of around 4 to 5 hours. So as you can see on the top are photos, and in the middle are classifications from our algorithm of the various thickness classes around the source site within a 10-kilometer radius of the well. So a few hours into the start of the experiment, you can basically just keep your eye on the red and yellow classes. Those are the thickest classes, and there, you know, is some of this in a stream going south. But in the middle of the dispersant release test, the next image shows a very obvious drastic reduction in the thickest classes, and therefore in the volume of oil that is actually present around the source. And then a few hours after they stopped injecting, and the next day, you can see that the large areas of the thickest oil have become prominent once again right by the source. So I understand that this data was actually part of the presentation to the EPA to justify continuing the subsurface dispersants, that they actually were quite effective, and our data, from again what I understand, was, you know, quite convincing that the technique works. So other than the test period that you just saw, we have not yet done any work with all those other days of flying over the source. And as you can see, and as was presented before me, there are periods of significant variation in the amount of injected dispersant. And some of them luckily correspond to days that we have data for. Again, the gaps in our covering the source, especially toward the right there into June and July, are not because we weren't there, but because during those times, there was a lot of interest in documenting and monitoring shoreline type oilings in different areas. And we just did not have the time during that particular day to fly back out to the source. But as you can see from the dots, there's quite a bit of data that's available. So we recently presented a proposal that I understand was accepted by the American Petroleum Institute to do just that kind of analysis with rigorous statistics to see if this kind of imaging has actually proven the effectiveness of subsurface dispersants based on calculating how much fresh oil volume, thick oil volume especially, was actually present around the well. So just some examples that sort of hint that the project may be successful. As I said before, the initial test, the flights that we did show you should concentrate just on basically the thickest class, the red class. So show quite a bit of very thick oil emanating from the source site. Once the injections began, especially in late May when the injections were quite steady, here's an example where you can see some thick oil still present, but definitely not as much as when no dispersant was being injected. And then some interesting cases later on, like imaging right after the dispersant was almost entirely shut off. The data show a very large area right by the source of freshly upwelled, very thick oil. And then another example toward the end when basically the largest injection rates were applied for a few days. Our data show that there actually in that time was no thickest class, meaning 0.15 and thicker oil features in the vicinity of the well. So that gives us some hope. Now, it's not going to be as simple as that because a number of factors have to be counted. I already mentioned the problem with the lag between the dispersant rate as measured on the bottom and potentially its manifestation on the surface. So we'll be doing of several test intervals to see how that affects everything. Of course, wind and sea state is another factor that we expect to have an effect by potentially pushing some of the surfaced oil down into the water column, and also by spreading it further away from the well site. And then also there, as you know, were a bunch of different activities trying to cap or clog up the well that may have temporarily flow and therefore the rise of the amounts of oil. So we have to carefully, time that in. The large containment dome, 7th to 8th of May, top hat, which was a smaller dome, mud injections, which were done with a nice name of Top Kill on the 26th of May, which we actually have documented because we were flying that day and there was mud everywhere. So that's pretty much what I have. The project has not started yet, so I cannot, show you any actual correlation results, but we're very excited to, be a part of this. Our work on Deepwater Horizon has generated several peer-reviewed papers in journals, and if you go on the company website, you'll be able to link to them and download them. So that's all I have.
Okay, great. Thank you, Jan. That was fantastic. So as I said at the beginning, we can stay after, but before we lose too many people, let me just mention next week what's going to happen. So same time next week, everyone who attended and got an invitation for this will get an invitation for next week's meeting. And as I said, we're going to focus on herders and in situ burning, so a different topic than we have the last three talks. And we're going to get three interesting talks next week. So tune in for look for the invite and tune in for next week. So for those of you who are willing to stay after a few minutes, we can go through some additional questions. And I'll start with a couple of questions, Jan. One question I have is, I remember when we first started talking about some of your work back in 2011, maybe the comment you made to me, because I had seen the May 9th, May 10th, and May 11th images. So we've looked at those images to see if there's a correlation with kind of subsea currents and wind and waves, and there isn't. But you made a comment to me about the region outside of the zone that you had the images from, right? Do you remember that, and how you told me that the entire region? I mean, I remember you saying you thought that the well had been capped and there was no more flow because the entire region had less oil on it. Is that consistent? Is that correct? And is that consistent with other times when dispersants were applied, or was coming up different places?
Tim, I don't remember what you're referring to. When we started flying, there was a lot of, as I showed, there was a lot of fresh oil, and then further away there was, emulsified oil, which means that it was probably several days old. As I showed during that test, yeah, it looked like there was nothing coming out for a while. So I think that's what you're referring to. Yeah. And like I said, that seemed to be very effective for the EPA and for other people. I remember NOAA's Bill Lair, who was the head of their prediction or modeling group up in Seattle. After those images came out, he called me and said, "Wow, I cannot believe the difference that it makes." Okay,
let me ask one more quick question, then we'll get on to some of the questions from the attendees. But one thing that we're interested in right now, and we're doing some work, is what is as a black oil slick, right? And your thermal images may help us answer this, right? Where a black oil slick is going to be heated compared to the surrounding waters, right? Because of when it's in the direct sunlight, especially in the middle of the day. Do you know, or can you look at your data where you have heavy, the red oil, and tell us with some accuracy on what the temperature of that oil is relative to the surrounding water?
Yes, absolutely. To less than 1/10 of a degree precision. So I didn't, I guess, mention this, during the talk, but what the property that affects all this is that petroleum has a lower emissivity than water. So if oil feature and a water feature have the same temperature, to the camera, the oil is going to appear cooler than the water by a few tenths of a degree. And that's what happens with the thin, relatively thin oil. And it also happens with thick oil during the night when there is no solar input. However, there is the solar heating effect during the day when at a certain thickness, which is usually about, for fresh oil, is usually about 0.2 or so, 0.25 millimeter thickness. That's enough for the oil to start retaining heat. and therefore flip the relationship where, you know, it appears warmer than water, and it truly is. And we did some very careful studies, both during day and night at the Omset facility in New Jersey, to basically better understand this whole process.
So how hot would black oil be in June in the Gulf of Mexico at noon?
Up to it was up to 5 degrees warmer than the water.
5 degrees warmer. Okay.
Mm-hmm.
All right. Well, let me see if I can look through some of these questions and ask them for you. Okay. Can you discuss the current state of science for using remote sensing to quantify oil thickness and volume? Where are we and where are we heading? Got any comments on that?
Well, we personally have some projects, some research projects that are continuing. I must say that actually throughout our entire career in oil spill research, if you will, there is somewhat of a paucity of both funding and you know, chances to do the research, which understandably is caused because you can't, with the exception of once a year in Europe, you generally cannot go out to the ocean and dump a bunch of oil and do a bunch of experiments. So basically the choices as we used are either the Omset facility in New Jersey, where for a lot of remote sensing techniques, there are limits to how natural you can actually make the conditions. For example, the tank is actually painted white. So short of simulating an oil spill over the sands in the Bahamas, you know, the white bottom reflects right through the oil and makes for unrealistic conditions. So we actually used blue-green tarps on the bottom to mask that. Then there are the natural oil seeps that we have used also. But to answer the question, there really isn't, both in America and in Europe, there is not as much research, i.e. advancement in this kind of technology as I personally feel that there should be.
Yeah, I would agree with that. I just, you know, when I think about it, right, it's very complicated. And I think Jan and his company and the methods that he uses is really commendable. The challenge with this whole thing is there needs to be really a lot of research, because, right, the chemistry and the change and the amount of emulsification and everything. So if you're going to start trying to figure out whether this oil is 1.1 millimeters thick over there and it's 0.2 millimeters thick over there, there really needs to be a lot of research, right? Because the oil properties change among oils. So these remote sensing techniques rely on differences in the oil properties, and those oil properties are changing as the oil weathers at sea. And then once you start adding water with emulsification, it changes everything again, right? So, and those are, and then knowing how much water is in the oil for how much the oil is emulsified is something that's really tough to know when you're flying over it. So it's really a complex issue, and the simple tests that we do at a place like Omset are maybe unrepresentative, as Jan said, but we may be testing an oil under just a few kind of different weathering states, and it is much more complicated than that. Let's see, another question. How are the capabilities of the imaging system affected by waves?
So back to Omset, as some of our viewers potentially know, Omset has a wave generator, which works very well. So we actually looked at that very question at Omset. The larger waves will stretch the oil film, and I'm talking fresh oil, not emulsified. Emulsified basically stays there, but the larger waves will stretch the oil so that it is actually thicker on one side of the wave than on the other side. So the answer to the question is more a question of what's the resolution of the actual data, the spatial resolution, because although waves do alter it very significantly on the basically the wavelength scale, and therefore you could see these effects on, say, 1 meter data, where, for example, the instrument that we flew, the thermal instrument we flew in Deepwater Horizon, had a resolution of a little over 4 meters. So my guess is at that point, and from the tests at Omset, basically the differences from one side of the wave to the other get averaged out within the pixel.
Okay. Okay. Here's another interesting question, and it's really kind of timely because there's the National Academies of Science, Engineering, and Medicine are doing a reboot of the Oil in the Sea. So I think it's volume 3 now, and they're working to generate a volume 4. So the question is, have you done any systematic flyovers to collect data to estimate natural seepage, for example, in the Gulf of Mexico or in other places?
Again, we tried to look at that question, particularly in California with the seeps in the Santa Barbara Channel. There are a couple of problems with that, if you will. So number one, since we work there so often, number one, the seeps, at least in that area, do not release oil continuously at the same volume or even close to it. For example, we and other people that have studied the seeps have noticed that during winter times, when there are major storms and therefore a lot of rain, the seeps tend to release more oil, and actually some seeps that seem to lay dormant prior to that started releasing oil. Whether that has to do with pressure from the subsurface water table, I don't really know. But the bottom line is the amount of oil varies. So we have actually gone there on certain days for our experiments, and in at least one case have completely struck out because there was very little oil that in the past 24, 48 hours had actually made it out of the seeps. So the answer is no, we have not tried to estimate the volume, but there are problems with trying to do it with a single day overflight because of this variation.
Yeah, I think that kind of burping of these seeps is consistent with the Gulf of Mexico as well, right? They aren't just kind of continuously flowing at the same rate. I hadn't heard that winter time is better. It's actually more active than summertime, but more pressure from the water table might maybe make some sense. But I would assume that maybe it's deep enough that the water temperature doesn't change that much between summer and winter. I'm wondering though, I know I've looked at seeps and the data to estimate volume seeps, and sometimes you gotta, the best literature is from like the 70s or early 80s, right? And there hasn't been a lot of recent. Do you pay any attention to that kind of literature, Jan? Is there any recent kind of estimates for the Gulf of Mexico that might be maybe more accurate and more and cover a larger area?
Well, I do remember that in the 90s, some researchers from Shell Oil were utilizing synthetic aperture radar imagery in the Gulf of Mexico to, number one, map the locations of the seeps, and then there was some effort to try to, estimate volume. But honestly, other than that, more recently, I don't know of anyone.
I wonder how big an effort would it be for you to take your instruments and go out and do a reasonable amount of the Gulf of Mexico to get an estimate of the amount of seepage? Is that huge, multi-million-dollar project, or is it something that could be done under more reasonable cost? Any idea?
I wouldn't say it's a multi-million-dollar project, but it definitely would need a healthy budget. There are, as we all know, pretty good maps now, again, primarily based on synthetic aperture radar data of the main seep locations. So that helps because we wouldn't need to just be aimlessly flying around looking for seeps. We could pinpoint specific targets. But depending on, there are, to my knowledge, potentially hundreds of seeps. So depending on which ones should be targeted, either regionally or in terms of size, it's primarily, I think, from the aircraft usage standpoint, it's a significant project.
Yeah. Yep. Okay, well, thanks. Let's see if maybe Doug or Mary, if you've gone back and seen a question that I missed, can you point that out? Because it's kind of the way the system works, it's a little challenging to go back and look at things. Is there,
Sure.
Doug or Mary, something else?
I haven't seen anything on the human health.
Okay. Doug, is there anything else that we need to?
No, there were a couple. I answered them with the typing the answer in.
Okay. Well, we're getting a quarter after. So I appreciate everyone staying, and there's a number of people that hung in there, so I appreciate that. I'm going to end the Zoom meeting here, and we'll hope to talk to you again same time next Tuesday. Thanks, everybody.
Thank you.
Thank you.
Okay, I'm going to stop recording, Doug and Lynn.